So welcome to everyone. Thank you for coming here. So it's a real pleasure to welcome Professor Ngai Ming MOK. Professor MOK is a chair professor and Edmund and Peggy Tse professor at mathematics at the University of Hong Kong, and he's an eminent, really eminent mathematician, well known all over the world for many, many outstanding achievements in several complex variables, complex differential geometry, algebraic geometry. He began his career in mathematics, of course, at Princeton University in 1980, and then he later went to become professor at Columbia University, at the University of Paris at Orsay, before coming back to Hong Kong in 1944, where he took the chair professorship at Hong Kong U, and he's also there director of the Institute of Mathematical Research at Hong Kong U. Now, as a measure of his eminence, he has served as on many editorial boards like many of us, but including journals, the prestigious journals Invenciones Mathematicae and Mathematische Annalen, who are really among the very, very best mathematical journals. He was an invited speaker at the International Congress of Mathematicians in Zurich in 1994. By the way, in Ngai Ming, I was also there, an invited speaker the same year.
Same time.
we did not communicate then. And he was also appointed member of the Fields Medal Committee for the International Congress of Mathematics in Hyderabad in 2010. Of course, he has received many outstanding awards like the Alfred Sloan Fellowship in 1984, Presidential Young Investigator Award of the United States in 1989, Croucher Senior Fellowship Award in 1998, State Natural Science Award of China in 2007, Bergman Prize of the American Mathematical Society in 2009. He was elected at the Chinese Academy of Sciences in 2015 and in the Academy of Sciences of Hong Kong in 2017. Last but not least, in addition to being, of course, fluent in English, Putonghua, and Cantonese, Professor MOK is fluent in French, German, Italian, Japanese, and he can read Spanish and Portuguese. So today, Professor MOK will speak about curvature and uniformization on bounded symmetric domains. So let's give a warm welcome to our speaker.
So first of all, I'd like to thank the organizers for the kind invitation and to Professor Serlet for the generous introduction. So the topic I'm going to talk about is on the interface between number theory and complex differential geometry. And this is precisely this interface that is what I want to indicate. Now, I should say that of course, what I have to talk about has to do with Shimura varieties, which is, of course, a big topic in arithmetic geometry. And I sort of got interested in portions of bounded symmetric domain, including Shimura varieties, right from the very beginning, from the point of view of differential geometry. But the interaction between the two was only came relatively recently. And as a matter of fact, the starting point of all this recent interest in this interface, it came from the study of the Andreotti conjecture. So if I take something like, I will explain a little more. So suppose I have a set of points. These are what one could call special points, points of complex multiplication. And then one takes the theoretic closure of this infinite set. The conjecture of Andreotti says that it is a finite union of connected Shimura varieties. So there's something like this is some omega prime, mod gamma prime containing it, maybe a few components. And so this is a question, of course, number theoretical in nature, and one would expect using methods of number theory. Now, then Sanier I think was around 2010, maybe slightly earlier than this. But he had an article with Pillar in which they have a scheme for reducing problems, not just under your conjecture, but also other conjectures like the Mumford-Manin conjecture on abelian varieties and so on, by a reduction into two parts. A first part, which is the typically, or which is basically number theory regarding Galois actions, and the other half is completely differential geometry. This has to do with the same problem. If instead of taking points, you take higher dimensional variety, replace these things by higher dimensional varieties. Yeah. And then you would like to look at the statistic closure of these things. It's more general than that. In place of taking this Shimura subvarieties, you can look at the following question. Yeah, so you look at something. Now this is, okay, so I will not take the, okay. Maybe I should explain the role of the uniformization. So there is some uniformizing map, so this is omega, so this is completely transcendental. And suppose you take something here, which is algebraic. What this means is that this sits as a domain in a canonical way, defined by inequalities, and you just take something algebraic and cutting through it. And you take its image might go like this, and then you take its statistic closure. Inside this omega mod gamma, let me call this x gamma, and then this thing has an algebraic structure. So you take its statistic closure. And then there is the so-called hyperbolic Ax-Lindemann conjecture, which says that in this case, the statistic closure itself is totally geodesic. Okay. Now, so this is a completely differential geometric statement. Although in the original formulation they use the term weakly special, and this is completely defined in terms of groups. But the equivalent is a statement saying that the image of an algebraic set by the uniformization map has a statistic closure which is totally geodesic inside omega mod gamma. So this is a completely differential geometric statement, having nothing to do with number theory. So this division of the problem then actually reduces the problem to two different directions of research. And as a matter of fact, I got interested in this prior to the knowledge even of, I didn't even, of course I heard about the Andreev conjecture. I didn't know any relation with the Andreev conjecture. I was led to consider such problems from complex differential geometry. Let me not point out how I exactly got into it, but it was from a completely different source. But then it turns out that the philosophy that I was proposing can be used to tackle this type of problems, and I will point out what could be done. But I want to start nonetheless with my perspective. My perspective is that of the perspective of a complex differential geometer, or complex geometry in general. When you talk about Shimura varieties, omega mod gamma, and gamma is a lattice, which is arithmetic. So it comes from, well, to start with, Shimura's definition of these things, and this gamma comes from essentially something like SPNZ and congruent subgroups, and then certain slices of them by requiring extra endomorphisms and so on. So then the lattices are special, and it's precisely because of the lattices are special, namely that they are arithmetic, they are just like integral points inside like SPNZ, for instance, in SPNR and so on. So there was a method which has been developed to tackle such lattices. And this is a method which is from a completely different field of mathematics. It's from logic. So this looks very, very different from what I was working on. So they have something called O-minimal geometry. And this comes from model theory in logic. Basically, they were studying other than, let's say, algebraic functions, they also look, and their quotients and so on, they also look at functions which belong to a bigger set, like some exponential real polynomial and so on. And this was made possible because in the case of arithmetic quotients, you have fundamental domains which are defined by inequalities having in them functions belonging to this bigger set, which replaces the polynomials. Okay, so there was a lot of activities, and now eventually leading to the solution of Ax-Lindemann. I will point this out. to which the method of logic or the method of model theory was brought into the action. So my perspective is quite different. I was looking at this as a geometric problem. I have no reason to assume gamma to be arithmetic. So as a matter of fact, my first work in this direction was in the rank 1 case, and where I just take any gamma such that Bn mod gamma is of finite volume. So this is basically a setup. So I will today explain what has been done, what could be done along this direction from a completely different geometric point of view, and then to explain how this is linked with the arithmetic cases and point out what questions could be addressed. So I'll probably prepare too many slides, but I will skip some of them. Okay. So first of all, everybody who had taken my course at Hong Kong University, we're very familiar with this. So moduli space of elliptic curves, you look at genus 1, compact Riemann surfaces, and they are parameterized by the lattices L tau. So L tau is, okay, so actually this is too bright. So this is the lattice generated by some point belonging to the upper half plane, and you impose a condition that is positive. You can always do that. And so the moduli space is very typical object on modular form. So what you get is that you take tau and tau prime. They would define the same equivalent lattices provided they are related by fraction linear transformation with the integral coefficients. So then there's this quotient I call x1. Actually, there are fixed points corresponding to the complex multiplication, but there's a so-called J function. The J function would give a one-to-one correspondence between this and the complex plane. If you compactify it, that's just one cusp at infinity, and this would give you the compact Riemann sphere. Now this has fixed, this action has some fixed point, but you can remove the fixed point by just defining something called level n structure. So what's a level n structure? So the moduli just now classify elliptic curves, but you can enrich the structure by considering not just an elliptic curve or the genus 1 compact Riemann surface, but also endowed with a certain isomorphism of the n torsion points with this should not have been here. So it's z mod n z squared. So you enrich the structure so that there are more equivalence classes. This introduction of more equivalence classes means that you reduce the gamma from gamma 1 to gamma n. Namely, you look at those which are congruent to the identity matrix modulo n. And if you take n bigger than or equal to 3, you actually get a torsion-free subgroup, and therefore you are looking into the geometry of the upper half plane modulo some torsion-free subgroup. And then this quotient will have finite volume and has negative curvature. So you're in the domain of objects of negative curvature. But actually, for the type of problems that the number theorists were considering, you can always reduce the problem to lifting by a finite cover. And so we can always assume without loss of generality that the group is torsion-free. Okay, so these are basically these are the congruent subgroups. The congruent subgroups, principal congruent subgroups. Okay, so this is just what I said a moment ago. Now, when it comes to several complex variables, then the compact complex tori need not have meromorphic functions. When they do, it means that there is an ample line bundle, and then one should not be classifying all compact complex tori, but rather those which are so-called polarized abelian variety. It would be said to be principally polarized when C1 to the power n of the lattice of this group, or rather this line bundle is minimal. So this would be called principally polarized. There's a technical definition, but which I skipped. Okay. Then there's an analog in higher dimensions, which is called the zero upper half plane. Zero upper half plane consists of those symmetric matrices, which are n by n matrices, and such that the imaginary part, which is real symmetric, is positive definite. These are the two well-known Riemann bilinear relations which defines the single upper half plane. And then one would be looking at this standard you can reduce also by introducing level n structures to get into quotients. Well, first of all, you have the symplectic group, so SP and Z with integral coefficients, and then you have the congruent subgroups. So the situation looks very much like the case of your picture. Okay. Okay, so these are spaces then of negative curvature. They have let's say negative holomorphic sectional curvature, non-positive holomorphic bisectional curvature, negative Ricci, and so on. So as manifolds, these are finite volume manifolds with properties of negative curvature in some sense. Now, the essential element in all of this is to look at, of course, the uniformization map. So this brings us into a domain of research which is called functional transcendent theory. Essentially, you're looking at objects which are algebraic, both upstairs and downstairs, and, but they're intertwined by the uniformization map, which is a completely transcendental function. So you look at objects which are algebraic on both places. Of course, this is the simplest type of problem that one can formulate, but there are, of course, more complicated problems. When one tries to solve, for instance, the Arx-Lindemann conjecture, and there you have the fixed RC closures and so on. So today, rather than actually, I should say that the subject or the approach of using complex differential geometry to solve problems related to the Andreev conjecture, so to speak, is actually just starting. So I'm pointing out what can be done and what needs to be done in the future. Okay. And if all this is completely, is completed, then actually you will be able to prove essentially theorems that have been established for arithmetic lattices by removing the assumption of arithmeticity. So this is a big program. Whatever theorem you prove using logic, you stay at I remove the arithmeticity assumption. But each removal of this assumption for a specific problem might require a different methodology or different solutions. So this is rather a program than a single problem. So Shimura varieties, by definition, would refer to the arithmetic ones. Okay, this is just a definition. Okay, so now let's come to analysis. So I want to use metrics. So first of all, I have to endow this omega mod gamma with a metric. And the metric that one endows it with is the Bergman metric. So to start with, take omega to be a bounded domain. And now you consider H2 omega the Hilbert space of square integrable holomorphic functions on omega. Take Fn to be any orthonormal basis. Well, actually, the n means different things. It's just an index. So you look at a certain kernel called the Bergman kernel obtained by summing over here. So this K is holomorphic in Z and anti-holomorphic in W. Okay. So then well, one checks that although I have to construct it using an orthonormal basis, irrespective of the orthonormal basis, you have the reproducing property. And such kernels having such reproducing properties on square integrable holomorphic functions are unique, from which one deduces, therefore, that actually you have the independence of the Bergman kernel of the choice of orthonormal basis. So this is a well-defined kernel. When you restrict to a diagonal, you get a Puris harmonic function, or in any case, you have a real function, and then one can then define, there should have been a bar here, Gij bar. You would then define a certain matrix, and one checks that this matrix is positive definite, and it comes from a simple, okay, so this is the Bergman metric. This is the Kähler form of the Bergman metric. So this is a Kähler form of the Bergman metric. And then, strictly speaking, one has to check its positivity, and its positivity is an exercise in one complex variable. if you take log of summation absolute value square of a sequence of holomorphic function, there's a so-called Lagrange formula in which the dd bar, or in this case just the Laplacian, can be expressed as a sum of squares. And then you just have to make sure that inside this absolute value, you can arrange things so that this is going to be non-zero if a point is given. So in several variable, you can more properly write this in the following form, but it's essentially the same thing. Okay. So you want to make sure that this sum of square actually, when you apply to 1, 0 vector, actually give you something positive, provided that you choose the FL and FK conveniently. You can do this because you can always, for a specific question, choose a good basis for its computation, knowing that the Bernoulli kernel is independent of the choice of the basis. Okay, so now I come to the topic of bounded symmetric domains. So the bounded symmetric domains are, well, these are classical domains which were classified by Elie Cartan. And this domain, the type 3 domain, actually this is biholomorphic to the zero upper half plane, just like the upper half plane is biholomorphic to a disk. So you do this by so-called Cayley transforms. And then there are two exceptional domains which are of type E6 and E7, and they are of dimension 16 and 27, respectively. So these are the formulas for the Bernoulli kernel in the case of the classical domains. And the important thing I want to point out is that actually all of them are rational functions. So it's important that I have rational function for a Bernoulli kernel. The Bernoulli kernel is an analytic object. It's expressed in terms of a real analytic function, and the fact is that in the standard coordinates, and the standard coordinates have been chosen, well, it's according to Elie Cartan already in the classical case, but in general one uses the Harris-Chandra realization, and then the kernel expressed there would be rational functions in Z and W bar. Okay, now I want to now bring in methods from complex differential geometry. Well, basically, the method is that of asymptotic geometry. So I can, for instance, mention one problem here which explains. I would point this out. Well, explain this later. So there's a question about bialgebraicity. So suppose I have, this is omega, and this is omega mod gamma. So suppose I have something, this is of finite volume. So suppose I have something algebraic here, and something also algebraic here. And I want to prove that this is actually a totally geodesic subspace. So this will be explained. Now, so the thing about a compact case, in the finite volume case, there's additional complication. So this is compact, so this is reproduced. So they are reproduced by using the group action. Now on the other hand, this thing is algebraic, so it goes out of the domain. And now you look at a good point here and look at a neighborhood and look at the asymptotic geometry of this algebraic object. The algebraic object is in particular as a variety of a neighborhood of a boundary point. So that asymptotic geometry will reflect the geometry downstairs because this piece is reproduced infinite number of times and goes to the boundary. So you look at the asymptotic geometry. So this allows us the perspective of studying properties of the quotient by studying asymptotic properties upstairs. And so this is asymptotic geometry. What kind of properties? Well, mainly curvature and connections and so on. Okay. So I want to explain this is just by way of explaining the method. This has nothing directly to do with the questions of Andre or with Art Lindemann. But just one way of looking at uniformization problems on a strictly pseudo-convex domain. So the ball is a strictly pseudo-convex domain. The domain is defined by an inequality, and strict pseudo-convexity has to do with the Hessian of the defining function. So this was an old theorem of Kambach's, which is computational. So what is a strictly pseudo-convex domain? Strictly pseudo-convex domain, well, the ball is an example of strictly pseudo-convex domain, but in general, you can have domains which are not convex, But then you can look at this, and this is a defining row less than 0, and you look at the hashing of the defining function. So you look at this, and you have strictly pseudo-convex domains. Okay, so on a strictly pseudo-convex domain, it's possible to write down a complete metric in a simple way, just by imitating the case of the ball. You remember, in the case of ball, the Berman kernel is very simple, and actually in that case, if you look at a potential function is essentially minus log. A potential function is a function by differentiating 2 times to get the metric. So this is essentially log of the Berman kernel. So it's log of the Berman kernel. And you imitate that, you just use the defining function row, and you have this guy. So you have this guy, and you compute its curvature. It's just a matter of computation. And the curvature turns out to be asymptotically -2. Okay. So what is the implication of this? Okay, now this is the curvature formula for the case of the ball. So this is curvature with the constant holomorphic sectional curvature -2. Okay. And of course, it means that the Einstein is Einstein, it's scalar Einstein, the constant is -n+1. Okay. Now I will just do a simple computation to to give you an impression why this sort of computational result could be established. So I will do a much simpler thing. Namely, I look at the potential function minus log minus rho and compute its Ricci curvature. So the Ricci curvature can be computed from log of the determinant of the metric. And when you compute, it's a straightforward computation. Nonetheless, there's important information contained here. Namely, when you look at this expression, okay, rho is a defining function. This is tangent to the boundary. So it grows like minus rho. And this is normal to the boundary and grows like 1 over rho squared. And therefore, when you look at n dimension, you pick up n+1 as the asymptotic behavior, this contributing to this side contributing to 1 over rho squared, and this contributing to 1 over rho to the power n-1. So they add up to n+1.
When you speak of domain, what do you mean exactly? Open set with
A domain is just an open set, a connected open set. But here, when I talk about strict pseudo-convexity, it is one with smooth boundary and defined by the defining function rho less than 0. So the model is a ball. The ball is absolute value z squared less than 1. So you take the defining function to be 1 minus absolute value z, absolute value z squared minus 1. So then this is an imitation of the ball, you may say. But you just write down something that imitates a ball, and you construct a metric using it by looking at a potential function which is minus log minus rho. And then the upshot is that this has asymptotically the same behavior as that of the ball. So this is a computation. But I'm showing some computation well, of course, this is more elaborate computation in the case of Klemm-Beck and having to do with matrices and so on. But if you want to look at just the volume form, look at just the volume form. The volume form can be computed in this way. This is a defining function, this is essentially distance to the boundary. You raise to the power n+1 and multiply by this guy. You get something here which it goes to 0. Because minus rho goes to 0 to the boundary. But this term, this is a tangential direction, tangent to the boundary. This is a direction normal to the boundary. And when you multiply, you actually get something which is essentially a Euclidean object, Euclidean volume form, essentially. So therefore, one can conclude the following, showing the volume form is like this. It's minus rho raised to the power n+1 multiplied by V0, which is a smooth positive NN form defined in the neighborhood of a boundary point. Okay, now when you compute the curvature, it's just computing the curvature of this guy, which gives you back the metric, and this guy, which is bounded, and this bounded object has nothing, is asymptotically negligible. Now, this proof, actually, although I'm just computing a Ricci curvature, with some modification, you can also give a proof of Klemm-Beck by slicing by one-dimensional objects. But let's not do it. Just to give you an idea that this computational thing can be done by explicit potential functions. Okay. Now, then I want to talk about one first result on uniformization. which was a theorem of Bun Wong. This goes back to 1977. So he was looking at strictly so-convex domain. This has nothing to do with the number theoretical problems I was talking about. So the question is, how do I characterize the ball among strictly so-convex domain? The ball has, of course, a lot of automorphisms and a lot of compact quotients and so on, because you have form lattices and so on. So suppose I have a strictly so-convex domain on which there is an infinite group of automorphisms, even countably, just countable set. Yeah. Then the Bun-Wong's theorem, which is quite remarkable, says that that already must be the ball. And the proof is the following. So so let me show the, okay. Now, there's a more straightforward proof if you make use of Pfefferman's result, which is the asymptotic behavior of the Berman kernel. So in the case of the ball, the Berman kernel just looks like the first half. But in general, when you have a strictly so-convex domain, you have some perturbation here, and these are functions which are of lower order. So this is Pfefferman's result. But actually, Bun-Wong did the proof first by making use of much more elementary things. So Pfefferman's theorem is a big theorem. It requires a lot of study of the behavior of geodesics and so on. But there are other invariant metrics. The Carr-Theodori metric defined by using bounded holomorphic function, which was much more elementary. And then he could also study those. So Bun-Wong was studying those Carr-Theodori metrics and so on. So there were different ways of reaching a proof of Bun-Wong, among which there are some elementary proofs, so to speak. And the argument is the following. If you make use of the Berman kernel, then just suppose I have an infinite group, and you take a point. You just take a point and look at its orbit under this infinite group, so it goes to a boundary, and you just compute the asymptotic curvature. The asymptotic curvature would be -2, according to Pfefferman's theorem, because the major part gives you -2. The other part gives you a perturbation which goes to 0. So the geometry, since you have an infinite group, the geometry at any point is reproduced at the boundary. And at the boundary, you have asymptotic geometry, which is that of the geometry of the ball. So this is the simplest kind of theorem you can deduce from asymptotic behavior. And you may take this as a sort of guidance. You are looking at the geometry of an algebraic set, and for that matter, not just algebraic, but maybe something analytic that goes beyond the boundary, by looking at its asymptotic behavior and reproduce and then conclude something about the quotient. Okay, so this I'm just putting in words what I was explaining. Now, since the asymptotic behavior is that of the ball, you conclude that geometrically this omega is ball-like, so it should be a quotient of a ball. But actually, there's no quotient. Actually, the group is empty. This is according to some result of Calabi. When you have a global potential function and it looks like a ball, it's actually a ball. Okay, so here is my input into the use of the KM metrics in a context which I will explain, related to this problems from number theory. So there was a question actually first raised by Clozel and Umo concerning holomorphic isometries. Their motivation was also number theory. They have some number theoretical question. They reduced the question to some problems in complex differential geometry. And then I solved their problem. And I solved their problem in a general context. They were interested in bound symmetric domain. In my case, I was looking at any domain. And provided that you have something, provided that their Berman kernels behave well. Okay. So the requirement, the statement is the following. Okay. So you look at two bound symmetric domains of different dimensions, possibly. And then you look at a certain holomorphic isometry, and there is also a normalizing constant. These are the Berman metrics. You allow a lambda, which is any real number, positive, and suppose this is an isometry of two germs of holomorphic isometry. So in other words, I'm giving you just a little piece of this isometry. And then the question is whether this piece or this germ of holomorphic isometry extends to the whole space, and whether it extends also beyond the boundary, and so on. So as a matter of fact, by the work of Calabi, this goes back to 1953, this was the thesis of Calabi, in which the famous diastasis was introduced. These are normalized potential functions for Kähler metrics. in fact, when you study the Berman metric, this is a case where infinite-dimensional techniques are useful. Take any domain, take an orthonormal basis of H2 of that domain. So this is an infinite number of functions, and you embed the domain, a finite dimensional object, into infinite-dimensional projective space. Then Calabi's results on diastasis and so on actually works in infinite dimensions, already stated in the article. So then we already tell you that after embedding the infinite dimensional space, you get an extension of this to the whole manifold. So as a conclusion, you would be able to conclude to say that actually you have extension within the domain, provided that you have to put in some small conditions about the Berman kernel. But in any case, you have extension. You have extension of the germ, or rather the graph of the germ into the graph of something on the product. So what is important, what's missing, is actually the boundary behavior. So does this go beyond the boundary? And this is precisely what they wanted for applications to the situation or to questions arising from number theory. Okay, so this is what I could prove. I won't have time to explain the proof, but this is what I could prove. You can always extend this to a rational function. Well, rather, should I say it this way? Make the assumption that the Berman kernel, both for the domain D and for the target omega, are rational function in zeta and C bar, respectively Z and W bar. Okay, so this is the case for bounded symmetric domains. It's also the case, for instance, of homogeneous domains in their natural realizations. When you have that, then look at the germ of map and look at the graph of the germ. So this is a germ of separability on the product. The statement is that, and then this extends to an irreducible affine algebraic separability. So it does not only extend beyond the boundary. And if the Berman kernel is rational, then the extension is algebraic. So should I say that the extension is as good as the Berman kernels? So impose some condition on Berman kernel, then you can say about the extension. Okay, so I put some additional conditions. For instance, you assume that the metrics are complete, then you actually get the extensions with the graph of a proper holomorphic isometry. Okay, so it extends to a proper holomorphic isometry such that the graph extends algebraically to the whole space. So this is the best you can hope for. And then one can construct examples which indicate that this is the best you can hope for. Okay. Now, so then there was some study about the holomorphic isometries between bounded symmetric domains. Now, if you take the domains to be of higher rank, then it follows already from my work going back to, well, on Hermitian metric rigidity going back to 1987, that actually there's nothing other than the known ones. So you have total geodesic isometric embedding. There's nothing more than that. So the interest is with the case where the domain is of rank 1, namely a ball. Now, I constructed, contrary to what was expected, I constructed some counterexamples in the case of n equal to 1, answering in the negative question raised by Ulmo and Clausel and Ulmo. But then for some time I was not sure whether they are high dimensional examples, until I hit upon an idea which was a little unexpected. It was possible actually to construct the image of a holomorphic isometry. And this construction goes as follows. I'm sorry, it might not be easy to read from far away, but let me draw a bigger picture. Because it's much easier explaining on the board here. Okay. So what is a bounded symmetric domain? You see that there are some inequalities. So just draw this as something with corners. So I want to construct something which is the image of a holomorphic isometry. So that's the theory of VMRTs I have been developing with Huang and other collaborators, in which we study minimal rational curves. Now this domain, for instance, you take a type 1 domain, it sits in something which is called a dual. So for instance, type 1 D1 PQ sits inside Grassmannian GPQ. Okay, this is inside. So on the dual space, there is a notion of minimal rational curves, which are projected lines on the Grassmannian, for instance. You take the Kluge embedding, and then in the image of Kluge embedding, there are still lines that lie inside the Grassmannian. Look at this set. So this is the so-called final variety of the Grassmannian. Then at each point, you have a certain direction in which you have lines shooting in that direction. And this defines what we call the variety of minimal-rational tangents. So here is a construction. So sometimes unrelated things become related after you have the proper interpretation. You take a point here. You look at the space of all lines shooting from there. Okay, like think about the Grassmannian. Now this thing has a singularity. So of course this cannot be the image of an isometry. As was proven there, the image must be something smooth. Okay, so this is not. But what I did was this simple argument. You just move this boundary to here. So you're pushing this. And what is this action? Well, this action is actually the following. I am moving by Möbius transformations. But moving by Möbius transformations is the same as moving by Euclidean translations. This one can check. So you're moving this. So in the limit, I will simply get something here. So just like a copy of this, but with a vertex on the boundary, on the regular part of the boundary. And this thing, what is this thing? This is by the limit of a sequence of Möbius transformations. And that means exactly it has a geometry of something which is the asymptotic geometry of this cone. The cone would actually, this cone, if I shoot from the center, what you get is actually the intersection of this guy with a certain ball. So when it shoots out, from the center, all you get here is strictly through convex. It's exactly the intersection with the boundary, exactly the intersection with the ball. Since the ball is strictly through convex, when you shoot it out, it's also strictly through convex. And now when you put it by Möbius transformation, the limiting thing as a set exists, and which is simply the cone with the vertex here. And then the asymptotic geometry, or the geometry of this is actually the asymptotic geometry of that. And this is strictly through convex. By convex computation, this is of asymptotic curvature minus 2. Therefore, in the limit, you get a variety which has curvature minus 2, holomorphic sectional curvature, and therefore it must be the image of a ball. So this is how I realized that you can have high dimension examples. And it turns out that these examples are very important when it comes to dealing with a question of Arch-Lindemann in the higher rank case, although that has not yet been worked out in detail. Okay. So these are examples of holomorphic isometry. Okay. So this is just a description. I already described it. I don't need to rewrite it. Now I want to give an example which is more related to the Andriot or to the Arch-Lindemann type of problems. It's the following. So okay. This is a study of the asymptotic behavior of a holomorphic curve. So it need not even be an isometry. I just study some holomorphic curve which goes through the boundary. So suppose I have a holomorphic curve. It goes out of the boundary, and I want to study the asymptotic behavior here. And the statement is the following. The statement is that actually it must be asymptotically totally geodesic. And this is not true in 2 dimensions. It's only true in 1 dimension. It's asymptotically totally geodesic. It is not so obvious how one could do it. It is much easier if it actually goes out in the regular part of the boundary. So I wrote a paper where I deal with this simple case where it goes out in the smooth part of the boundary. So you still need some asymptotic study of the curvature, but it is much more complicated when it goes out from the corner, because the boundary is very complicated actually. It's intersection of many things. And when it goes out inside in the corner, it's very difficult to analyze, to do this argument analytically. And rather, I make use of this rescaling argument. So think about Bunwang's theorem. This is actually a rescaling argument. You take a sequence of points going to the boundary, and you pull it back. So you rescale by using automorphism. By rescaling, I mean that you pull back by some automorphism. So what I do is an argument by contradiction. So suppose I have something going out, maybe it's more suggestive that I say that the boundary is not here, It's not going out here, but rather that it goes out here. So it goes out, so some corner. So it might go out some corner. So this is the argument. Now, although I draw just one point, actually this is a curve. And there are good points on the curve where things are smooth and so on. So I look at this and I rescale by automorphisms of the domain. So the point is pulled back, the point is pulled back, and pulled back. Now, it is easy to see that this thing with the as a Riemannian submanifold as asymptotically constant curvature. That's quite easy to see. But to have asymptotic constant curvature doesn't mean that it's asymptotically totally geodesic. It might be that the second manifold is a constant, asymptotically some constant. So what we did was the following. You pull back by automorphisms until you get an isometry. By passing to limit, you can get an isometry of a disk. And also this isometry has very special behavior. All the geometry looks like a geometry at one point in the boundary, asymptotic geometry at one point in the boundary. But of course you have to make that precise. So then by this rescaling arguments, I do by extraction of convergence subsequences a very special holomorphic isometry. It is almost a homogeneous one. You want some property to be valid on the whole holomorphic curve. You just have to specify what it is, and then you pull back by a sequence of points going to that point. So in some sense, at least philosophically, you can construct something homogeneous. It's not quite there yet, but suppose you can construct some homogeneous. But then you still have the question. There does exist homogeneous embeddings which are not totally geodesic in the case of positive curvature. Take the Veronese map. The Veronese map is an embedding of Pn into a big N, and which is an isometry, but which is not totally geodesic. The second manifold, the norm of second manifold in this case is a constant. So what distinguishes positive curvature from negative curvature? So it's not so clear. How do you make that distinction? So here, let me give the argument. Okay, so these are just, consequences from the first statement. So what I want to say is that it's asymptotically totally geodesic. Let me derive conclusions that are useful for the Arcs-Lindemann type of theorems. First thing is that if you have a holomorphic map which is equivariant, then it must be a totally geodesic. So there's nothing like the Veronese map in the case of negative curvature. Okay. As a conclusion, as an implication of the result. Well, you can reduce this question to the situation where D is just a disk. Because on the bound symmetric domain, there are many geodesic disks. There are geodesic disks of different types. When you restrict to enough of them and you polarize, you will see that this implies the theorem for the case where D is of higher dimensions. Okay. Now, so after reducing to a case where D, so this is just the reduction argument. Okay. Now, so all of this, I should say that in the previous slide, in the classical case, this was done by Clauzel by a computation using Lie theory. But in the exceptional case, this computation fails. Okay, so this is just putting down in words what I already explained here, just taking a sequence of points and rescale by bringing everything to the center, so that you have a sequence of maps instead of one single one, and you pass a limit by kind of Montel theorem for holomorphic isometries, and then the limit is still it will be a holomorphic isometry. Okay, you don't have to read that much, but you just have to see the picture. You're just pulling back and trying to extract convergence subsequence. So the upshot is, for the lack of time, let me just explain what it is. As I said, you want to get a property of the limiting holomorphic curve which reflects behavior at a single boundary point, a judiciously chosen boundary point. The boundary is a curve. You have to avoid certain points, but if you choose a generic point on the boundary, that has certain asymptotic behavior. For instance, the absolute value of the second fundamental form would converge to some constant. You want to prove by contradiction, assume that to be non-zero, and you try to derive a contradiction. Okay, this is the picture. And now, now then I have a holomorphic curve. Let me magnify the picture a little bit. So let me draw this not as a curve, but draw this as real surface. So this is the image of a holomorphic isometry by extraction. And here I would have at each point a tangent space. And I want to say that it has properties looking like a homogeneous map. So what I need is actually to say that all the tangent vectors are equivalent to each other. So when you are in the high rank situations, in the Bohr situation, all directions are the same. In high rank situation, of course, that's not. So, but this way of construction allows you actually to construct something which is sort of uniform geometry in the sense that all the tangent planes are equivalent to each other under the automorphism group of the manifold. And how does one do this? Well, you have for tangent vectors something called a normal form. So you can put it in matrix form. So some diagonal, you can put it in matrix form. And then there's a normal form but these are real numbers between 0 and 1. And they are descending. Then this is a well-defined normal form for each tangent vector. But this looks like a bad function to study. You have to take soup and so on and so forth. But you can actually recover properties of the normal form from the properties of some Hermitian bilinear form coming from the curvature operator. So you look at characteristic polynomial defined by the curvature, and then this is sort of an algebraic or rational function defined in the neighborhood. And provided you choose a good point, these things would have at the boundary certain behavior, a well-defined value, and you just pull things back so that things reflect properties at that particular point. So this is what you would get. You look at so you look at the eigenfunctions of the symmetric polynomial. Yeah, you look at characteristic polynomial, and then you look at eigenvalues. Okay. So then, believe me that this is something that you can carry out yourself. So you can have something which looks like homogeneous. It's not homogeneous, but it looks like homogeneous. Okay, so let me skip this and just. Okay, so I have. So this is the statement that all the tangent lines are equivalent to each other under holomorphic. So I have a hypothetical. Very nice holomorphic embedding, and I have no conclusion that one can draw from there. Okay, this I can skip. This was the origin of this. So I want to say that among the bound symmetric domain, there is something called the tube domains. And the tube domains are characterized by the fact that there's an invariant hypersurface in the tangent space. Okay, and this is the list of all these with an invariant hypersurface. Take type 3 domain or type 4 domain, you can define using a determinant, some invariant hypersurface. In general, you cannot do it, but you can do it for certain domains. Okay, but this, I didn't define this type, so let me skip this. Okay, so total geodesy of certain curves on the tube domains. So it's this. So suppose I have a certain, a nice, well, that's uniform curve. And if I have a uniform curve, then because there's a hypersurface corresponds to some line bundle, and then there's some section which is now uniform, this is a constant. So this is the Poincare-Lenoir equation. The Poincare-Lenoir equation would have on the left-hand side 0 because this is a constant. On the right-hand side, you would have the curvature function and also the second fundamental form. Or you have the Gaussian curvature coming from the curvature function of omega and also from the second fundamental form. It is by means of this type of inequalities I prove some results earlier on characterizing the geodesics in tube domains, on quotient of tube domains. And it's by exactly that argument, but now applied to this uniform curve, that I can get a conclusion unless this guy actually comes from a totally geodesic curve. So I made use of negative curvature in a precise way. In the case of tube domains, you can actually have some line bundle, and you have the Poincare-Lenoir equation, this precise form, and you can do it. Now, in order to get the theorem that I had with Chen, one would have to embed things inside tube domains. This is not obvious. I give you a domain, I give you a curve, you can get this very good curve. And this argument will work if this curve lies inside a tube domain. Not only that, but that this curve has maximal rank at every point. Then I apply the Poincare-Lenoir equation, that would be it. Okay, I apply the Poincare-Lenoir equation to the curvature function, or this norm of this section of some line bundle, and I get a contradiction by just a Poincare-Lelong equation, by computation. But in general, what you have to do is, this might not be of maximal rank, so you have to embed. If it's of lower rank, then you have to insert something of lower rank. And if it's not a tube domain, you have to insert some tube domain into it. Suffices to say that these two problems, which are sort of non-typical integrability questions, because you have to insert something. It's not just integrating the distribution, but you have to insert something of intermediate dimension inside it. And this can be solved precisely because I'm on a balanced symmetric domain. On a balanced symmetric domain, the curvature operator is parallel. So I have to make use of the parallelism of the curvature in order to insert something. So I will just show you the slides, but so this is a statement telling you that you can insert some submanifolds for which you can apply the Poincare-Lelong equation argument. So there are two parts. One is where you can insert something of maximal rank, but the second thing is that you can insert a tube domain inside. So they run along sort of parallel arguments. Okay, so let me skip this. So now comes to a theorem which is then of the nature of bialgebraicity. This is related to the Arx-Lindemann theorem. Okay. The statement is this. This is actually the analog of the Arx, the result of Ulmo-Yafayev in the following. Suppose you have omega mod gamma, and let's state this for the compact case. Actually, by now we are able to do it with the finite volume case. But let me explain this only in the compact case. So you take, this is a uniformizing map. You take something algebraic here. A gamma need not be arithmetic. Okay. So you take something here. And suppose the image is also algebraic. So these are so-called bi-algebraic sets. You have the uniformization map, which is transcendental, but there are objects which are algebraic on both sides. This is the case for geodesics. Okay. And the theorem here says that, well, these are the only possibilities. So this was proven by Ulmo-Yafayev in the arithmetic case. But in the arithmetic case, what was used was a very strong result due to Delin and André Delin. This has to do with Hodge theory. Even in the finite volume case, even the mixed Hodge structures, and it's a deep result, and which only applies in the arithmetic case. So then what you can do is, okay, so yeah. So the theorem is that actually, actually this implies it's totally geodesic, but also there's a stronger theorem because I only have to look at this algebraic set. That does not need to be something of finite volume in the background or compact in the background. What's essential is only that the subset is of finite volume, or as presented here, the subset is compact. It might be a compact thing sitting inside something of infinite volume. So the result is stronger in this sense. Okay. Now, okay. Okay, let me just say a couple of words about the method. Okay, so I have a domain, and I have a group action, and the image is actually something algebraic. And I want to prove that this is totally geodesic. This is what I want to prove. So how would I go about proving this? Well, suppose I can prove that it's homogeneous. So I certainly have some infinite group acting on it. But if I can prove that this infinite group generates something which is continuous and which acts homogeneously on this, then you're done. Then you're done. This is sort of classical. It goes back to the result of Kusul and a number of people, where well, something like this, admitting a compact quotient or even a finite volume quotient and homogeneous must necessarily be bounded symmetric domain. It must be symmetric. In other words, the automorphism group must be semi-simple. And then also this embedding must be also totally geodesic embedding. Certainly from what we knew. So once you can prove that this is homogeneous, you're done. But to prove that it's homogeneous is quite difficult. You just have some infinite group. How do you grow from an infinite group to something homogeneous? So what we did was something intermediate. We didn't prove that it's homogeneous. We proved that it's in some sense pseudo-homogeneous. In other words, you have a group acting on it. You complexify the group. The group acts on a bigger space. Right? You have a compact dual. The complexified group acts on the bigger space. And then you move a point by this bigger group and it will go out of the space. But you want to say that if you take the orbit under this group, this will recover by taking intersection with omega, you will recover this set Z. So this is what we did. And of course, there are several steps for proving this. And then well, after proving that this is pseudo-homogeneous, we still have to prove that this eventually is a balanced symmetric domain, which is totally geodesically embedded. And there we make use of Nadal theorem. The Nadal theorem in the compact case. The Nadal theorem is the following. So let me just, I will skip the steps, but simply say what Nadal theorem says. So Nadal, first Sig Franco and then Nadal were studying the automorphism groups of uniformization or universal covering spaces of complex manifolds, and then later also finite Fourier quotients. So Nadal theorem is the following. Suppose you take a compact Taylor manifold with an ample canonical line bundle and denote by the uniformization map. Then the automorphism group of X tilde, this is universal cover, is a semi-simple Lie group without compact factors. It might be trivial. It might be trivial. So in other words, if it generates a one-parameter subgroup, then this subgroup, or high-dimensional subgroup, the full group would be semi-simple. There's no unipotent radical. And also there's no compact factor. So how is this make use of? Well, certainly, but this allows one to say that although I don't prove that this is homogeneous, I look at this semi-simple factor, and I look at the embedding using this semi-simple factor on a point, at the orbit of a point, then this need not be complex, but this is real. But it's real homogeneous. At least some orbit is going to be a real symmetric space, embedded isometrically into it. Then you have at least 1/2 the dimension, because by complexification I will get something homogeneous. So you have at least 1/2 the dimension, and in one special case, then essentially it's the complexification. So you have this well, you take the orbit under some continuous group containing the infinite group. Okay, so you have something which is Riemannian symmetric, and which is at least 1/2 the dimension. Let's say it's exactly 1/2 the dimension. Then you will have on this this set Z something which is 1/2, and then the geometry of this 1/2 can give rise to something that's defined on all of that by complexification. This is possible. And after that, you will have on this domain a certain bilinear form. This is what I call a holomorphic complex Riemannian metric. It's not a metric, it's actually a quadratic form. So once you have that, then you will be able to make use of Chern class inequalities to get some contradiction. So to say it simply, in this particular case, suppose you have actually this complex Riemannian holomorphic complex Riemannian metric, then the first Chern class is 0. Because there's a duality. So the tangent bundle is isomorphic to its dual, and therefore the first Chern class is 0. On the other hand, this is a submanifold. The Chern class is negative, so there's a contradiction. Now, if you have a more complicated situation, you can still make use of K-line symmetric to conclude. So one final point I want to make is that I have, well, I wanted to say the link to the functional transcendent theory, and this is a joint result that is put on the web. Okay, now this is just the statement of Umo Yafayev. Okay, maybe I should say one word about this. So this is my result in the rank 1 case of the Ax-Lindemann conjecture without arithmeticity. So I make use of asymptotic behavior of curvature, and also I make use of foliation theory to prove the same result for non-arithmetic lattices, or not necessarily arithmetic. It's independent of works in O-minimal theory. And as a matter of fact, the first result along this line I proved was back in 2010, where I considered a case of geodesics. Okay, let me skip this, but so this is the result that has been put on the web, and this is a solution of the so-called Ax-Chanouel conjecture in functional transcendent theory. So actually, Zimmermann was visiting me in 2016. We had some earlier communication at the time when I produced this result for the Ax-Lindemann in the rank 1 case. And then we had some discussion when he visited me. And this is the so-called Ax-Chanouel conjecture. The Chanel conjecture is the following, is about the characterization of subsets with excessive intersection. So you look at the graph. Okay, you have the uniformization map. You have to look at the graph. And then in the product, you have algebraic structures, and you can look at algebraic things intersecting them. And then the intersection will have some certain expected dimensions. You just count dimension, right? The two curves inside a surface would intersect at 0 dimensions, and so something like this, right? So you have some expected dimension. The conjecture was the following, Arc-Chanel, is that if the dimension of the intersection exceeds what you expect, then everything comes from a totally geodesic subspace. So essentially this is what it is. So now the proof of this is then a combination of two perspectives, the perspective using foliation theory and asymptotic behavior and so on, and the perspective using O-minimality theory coming from mathematical logic, as I explained. So at this point, this is not a pure proof. So this proof makes use of different components, so contribute from different sides. But as a matter of fact, even in the case of the O-minimal theory results, they had to make use of behavior of volume estimates on subvarieties on symmetric domains, and this was the result of Jim Huang and Wing-Kam To. And they do this by making use of course, Kähler geometry. So this is sort of a combination of different techniques coming from, well, the complex differential geometry, Kähler geometry, and then foliation, and then the O-minimality theory, and then also Hodge theory, because one has to make use of André Delin. So this is really interdisciplinary. It's not interdisciplinary. We are not talking about physics and math, but we're talking about inside mathematics. You have really a set of different techniques being used. So ultimately, we would like to prove the theorem without arithmeticity, and then we have to replace whatever is done using methods of number theory or logic by making use of methods of complex differential geometry. We have not yet been, this is ongoing process, and we'll have further results in this direction. But let me say this thing, what is the meaning of this theorem? But just the statement here, the statement is that Arc-Chanel actually implies Arc-Lindemann, and that was one of the reasons why this is important. This intersection theoretical formulation, a conjectural statement, once proved actually implies Arc-Lindemann. Arc-Lindemann is a very special case of Arc-Chanel. So let me stop here.
So, time for questions. Anyone? I have 2 questions, but maybe someone in the audience has some question first. One is, for instance, the last theorem that you showed about these bounded symmetric domains.
Yeah.
Now, these are results that are, of course, with complex matrices. But is there any, from all these results, say a Riemann surface, say can be considered as a real surface,
yes,
double the dimension. So these kinds of results, do they have applications in the real world, if I could say, for real matrices or these kinds of things?
So you're talking about the results on
the last one, yeah.
The last one.
Yes.
The Arc-Chanel.
Yes.
Yeah. Okay. Now, first of all, in the real situations, the intersection may be less than expected.
Mm.
In the complex case, it's always bigger than or equal to some expected dimension. So in the real world, something happens that would disappear in the complex. So one can try to formulate something, but it seems to me that one has to put conditions on the intersection a priori. That it doesn't also, for instance, you can go below the dimension, and then there's some excessive due to the fact that you have total geodesy and they compensate for each other, then it's not so clear where the source of this change of dimension is.
Yes.
So not a straightforward formulation.
I see. Another but naive question. So you use like torsion, curvature, etc., all these from differential geometry.
Yes.
But do you define them simply by the same formulas as in the real case, or you double the dimension to be with real?
No, actually, just formal definition. So you just take the think about Riemannian metric, but allow everything to be holomorphic. So you double the dimension, but the formulas are the same. So the connections are the same, the portions are the same, and so on. So it's formal, and therefore what you get is something rational. So you just look at the formula for the balanced magnetic domain and double it.
Other questions? Yes.
So besides the results you apply, but I would like to ask is the methodology that you develop actually could also apply to real mathematical problems like application problems that could simplify the problem much more. So could you give those examples?
So at this point, there are different groups of people working on this. So we are supplying, so to speak, the necessary, or giving proofs of the necessary theorems. And for instance, Arc-Chanouel has now been made use of for applications in number theory. And some of these articles have appeared in the web. Yeah, actually. So of course, Arc-Linnemann, for instance, was sort of formulated as an intermediate step for proving the Andreault conjecture. So there's some generalization of the Andreault conjecture which can be implied by the Arc-Chanouel. You can look up this work by Dorr and Ren, which is on the web. So some application of it, and there will be more applications in the future. Also, I'm just writing this for the simpler case of our results. There are other results involving the derivatives of the uniformization map. So.
Other questions? Then if not, I think we should thank again our speaker.